Okay, the last time we already done for the transistor DC bias. That means the transistor, they need the DC power to make it work. Okay, and we're using the transistor for either the amplify or the switching. Okay, and any question regarding into the DC bias? That means when you're looking into the circuitry, you know right away, is it the NPN or PNP? Okay, and also you already know how to do your DC calculation, especially for voltage divider bias. That's what we concentrate on. Okay. If you have no question, today we will be stuck with the AC for the transistor. Okay. So the first we can see in here, they're talking about the capacitor. Okay. For your guy must be remember, capacitor will be open for DC. That means the capacitor, when they full charge it, they not allow any DC current flow through it. So that's why capacitor will be blocking DC. However, for the AC, they allow signal to get through it. Okay, that's a very important thing. And normally, last time we already said capacitor, when they connect to the AC circuitry, they get the resistance. And that resistance calculated by IC in this formula right here. Okay, 1/2 pi times F times C. Okay. So basically, the resistance vary with the frequency. Okay. And the next, they're showing you this is a shorted. Okay. And this will be open. So the capacitor, they open, that means no current can be flow for the DC. But they short, that means they allow the signal. For example, the sideway, one side, they can go to the other side. So they say for AC analysis, the capacitor is shorted. For DC analysis, capacitor is open.
What was the 0.1 R referencing?
Now, that means for good coupling, that means you have to select the resistor, okay? So IC will be less than 0.1, the value of resistor. Then you can get much better for coupling.
To allow a better charge rate?
Allow the signal to be clean it when they pass through the capacitor.
Right, I think.
Okay, so next one will be an amplifier analysis. This, to the technician, you don't have to go too much detail. That's for engineering, okay? When they try to design transistor for amplify, okay? So perform a complete DC analysis. That means before you want to do an on AC, you have to do all of the calculation needed for the DC bias That means you have to know what the VB, VE, VC, IB, IE, IC, and VCE. That means on the DC calculation. Okay. Then we start with the AC analogy. So in order to do it, first thing, they say you must be shorted, okay, on coupling and bypass capacitor. What that mean? That means on the AC, you never see any capacitor, okay? The thing is capacitor will be shorted for AC, so they not display on the AC circuitry. Visualize on DC supply voltage at AC router. That means all of the power supply DC must be route. Then you replace the transistor by either pi or T module, okay, and draw AC equivalent circuit. That's what, if you want to analyze AC, then you have to follow that step by step. Now, this is one of the T module. So you can see the green one here. Okay, there's a green one here. Substitute for the transistor here. That means in AC, you not draw this transistor anymore. You have to draw this module. This is the base. This is the collector, and this will be admitter. Now, you can see in the collector, you get the current IC going to the transistor. And at the base, you get the current IB going. And you get the current IE leaving. However, in the AC, between the base and the admitter, you not see any more diode. You see that? You don't have any diode here. And they substitute by R prime E. What that mean? That means the internal resistance between the base and the admitter in the AC configuration. So in the AC, the diode from the base to the admitter will be substituted by the resistor. And that resistor will be R prime E. And they will be doing calculation by this formula. R prime E equal 25 millivolt divide DC admitter current. That's a formula, okay, for bipolar. If you want to calculate the value of that resistor, then you take 25 millivolt divide to IE, okay? And also in here, they say the resistor of the base, G in mean impedance. Some textbook they're using R base, resistance of the base. Okay. If I want you to measure the resistance from the base, okay, then from base to what? If I want to measure R base, RB means resistance from the base to where?
Ground.
To ground. Remember, when we're talking about only single point, that means from the base to the ground, you measure the resistance, okay? And On this hand now, they're using V in, same thing RB, doesn't matter. And the formula for the Ohm law, that will be equal V at the base divided to the current IB. That's why you get RB. Okay, so in general, that will be VB divided IB. I already talked to you. They're using an uppercase for DC. They're using a lowercase for the AC. Okay, and the next formula here, VBE. What that mean?
Voltage from base to emitter.
Exactly. That means the voltage from the base to the emitter. That means from here into the emitter here. So they will be equal to current IE times R prime E. And then they can say, okay, J in B now, they will be VBE, that means this one here, divide IB, okay? Or they can give you this formula, okay? Beta times R prime E. If you want the input resistance from the base to the emitter. Okay, any question on this thing?
And so beta is, let me look at my notes for here. Beta is the ratio of the collector current to the base current. That's how you would find beta?
Yeah, still beta IB.
Okay.
Same thing, the same thing.
Sweet.
Sorry, I'm not following what that comma thing indicates. The little mark above the R. What is that?
Quick one.
The
prime.
The prime. Oh, prime. Okay, I got you.
Yeah.
Okay.
I think that's just standard notation for equivalent resistance. It's a small signal resistance.
Thank you.
Hey, Mr. Pham, is there a difference between AC beta and DC beta?
That's the difference.
Okay, thank you.
Right now, we're talking about AC.
Right. So,
Only thing what I emphasize here, make sure you at the base, at the collector, you get the current going to the base. That
So
will
what-
be IC.
so what did you say the AC beta is equal to?
AC beta.
Right. What is it equal to?
No, equal the same thing. Normally, they can give you 150 using for both. Okay, if they want to separate it, then they can tell you the beta for DC and the beta for AC.
But otherwise, it's the same.
Yeah, otherwise you're using the same.
Okay. Thank you.
Okay, you know.
Just one question. Going
Yeah.
back to the beta. Now, isn't beta equal to IC, IB over IC when we're looking at DC?
IB over IC.
Right. Beta is equal to that, right?
Beta will be equal IC over IB.
Beta is equal to IC over IB, right? But over here, when they substitute that in their beta, is IE over IB.
IB over.
IE over IB, isn't it?
No, I didn't say.
So you when you say Z,
The third line.
the third line. And the
First line here, right?
yeah, third, number 3, line 3 and line 4.
Okay, now. Line 3 here, right?
Yes.
Okay. So you want to go into a little detail here. Okay. VBE equal RE times R prime E. Is it okay?
Yes.
Okay. So the G in base, they substitute VBE
Right.
equal that one, right?
Yeah. Right.
Okay.
The next line.
The next line, basically in here, you understand they try to ignore IB now. If in this formula, IE equal what?
Well, it's basically saying beta is equal to IE over IB, isn't it?
Now, what IE equal? IE equal 1 blood
Beta.
beta IB, right?
Right.
Time R prime E.
Right. Okay.
Then they cancel IB here and IB here.
Okay.
So basically, there have to be 1
Plus.
beta time R prime E.
Right.
But the thing is in the book, they ignore 1 blood.
Because
So
beta.
that's why they don't care that one.
Right. Because beta is usually a lot bigger.
Yeah.
Okay. All right. That's fine. Thank you.
Yeah.
Hey, Mr. Pham, so after all of that, I guess maybe I missed something. What is the exact formula for beta, AC beta by itself?
Right now, if you're looking into that module, I expect you can able to understand if you want to calculate the resistance at the base, then you can using beta time R prime E.
I guess what I'm asking is I'm asking for a formula. I don't know if there is one, a formula for beta only, AC beta, AC beta.
No, I said AC beta or DC beta depend. If they given you one beta you're using for both DC or AC.
But in this case, we're studying AC now. So that's why.
But what I'm saying, if they given you the beta for AC separately, then you're using beta for AC.
If they did not give you the beta for the AC, how would you find that out?
Now you're using the same beta for DC.
It's on the data sheet for the transistor.
Yeah, if you go,
It's not an intrinsic thing. It depends on how the transistor is fabricated, I think.
they not.
Yeah. My question was, I don't want to drag this on, but my question was, I was just like there's a formula for the DC beta, I was wondering if there was a formula for the AC beta.
Okay, they can given you a beta and they say DC 100. And also they can give you beta for AC 80. Then if you want to calculate for AC, you're using beta for AC. If they not given you this one, you're using 100.
Like I said, Mr. Pham, I'll let it pass. But my thing was, I was trying to find a formula. I know for beta DC.
Formula.
Joe, Mr. Smith,
Yes.
think the formula is the same, okay?
Okay, that's okay. That's what I need to hear.
Change depending on what they give you.
Okay, so the formula is for AC beta is the same as the formula for DC beta.
Well, how about voltage current?
Beta is a value that depends on how the transistor is fabricated. Its doping
Yeah, the quality
profiles.
view. You know, that coming from the manufacturer. Okay. And now this is general. If you get the amplifier, they get the gain 200. And if you want to calculate the VL, the gain of the amplifier, to check the ratio between output and the input. Okay, now this is the first one will be a CE amplifier. So you can get the CE amplifier, CC amplifier, and CB amplifier. Okay. Common emitter amplifier. When they say common emitter, then the circuitry emitter will be routed. Okay. Common collector. That means the AC collector will be routed. And common base, AC, the base will be routed. Okay. So now, when you're looking into the circuitry, you must be recognized. Is it a common emitter or common collector or common base? Okay. And the relation between the output and the input, that's very important for you. Even you don't have to go into detail to do the calculation. Okay, so we already telling you here, common emitter input will be applied, there's the input here, applied to the base. Output from the collector here, okay? And also they're telling you input output will be our phase, 180 degrees, okay? That means input output will be opposite, okay? Input positive, output will be negative. And if input negative, output will be positive, okay? Now, we're first talking about capacitor. This capacitor, the name will be a DC blocking or AC coupling. Okay, that is the name. Now tell me the purpose. How come you need this capacitor here?
Block DC.
To store the energy? I don't know.
No,
You want the signal to be able to go all the way through and not go to the ground.
no.
No, you block DC and pass AC.
You see, I said C1 DC blocking,
Right.
AC coupling.
AC coupling means the AC component can get through, but the DC component won't.
Exactly. Now,
Same with C2.
amplifier. But they want to amplify. This is your void right here. Okay? Your void coming in.
Right.
Okay? And they want to amplify your void, make it bigger. So we need the capacitor guarantee no DC from the source here can get into the amplifier. So that's why they must be blocked. However, your void they are allowed to go. Okay? Second,
DC or fire the generator too, right?
In some case, if they get DC, okay, normally you don't. But in case they get DC, they must be blocking. The next one, C2, same name, same purpose. The thing is, you understand at the collector here, you get two different voltage. The first will be the voltage DC bias for your transistor working. And the second, you can get your voice coming from here. Okay? So when they going out, the load here means the speaker. You don't want any DC go to speaker. So that's why this capacitor here block any DC at this point. Only AC will be coming out. Okay? And the last capacitor here. The
Bypass to go around the resistor, you know?
bypass. Okay. Bypass. What? Bypass. Bypass what?
RE.
Exactly. That means on the AC current, when they go up to this point, they not go down here. The thingy capacitor will be shorted. So the current AC go here to the ground. Okay? So in the AC, if you measure your void in here, you get 0. The thing is they shorted to ground. So that's why the name of the C3 will be bypass. And they can asking you, bypass what? Then you have to understand, bypass this meter resistance. That means in AC current cannot flow through this resistor. They go to capacitor short to ground.
That resistor RE is only for the DC.
Right. That's for DC.
Question, Mr. Brown.
Yeah.
Regarding the current that flows to RE, what is the AC current or the AC signal doing to the current after it's been bypassed to C3? What is occurring to, what is the current state? What is the condition of the current when it flows into RE? Why is it different if the AC signal is bypassed? Is the current cleaner? Is it stronger? What's
No, that doesn't matter. If you get a sideways here, they go into here. So they get the current. The current when they go up to this meter here, okay? AC current, this capacitor, they already shorted to ground. So that current IC will be go to ground, not go to this guy. That's why they call a bypass.
So that resistor has no current and no signal running through it. It all goes to the capacitor.
Or AC. Look like they open. Okay, now, what is the difference between bypass or not bypass? If you don't have a this capacitor, then AC current will be go to RE. If you get this capacitor, the current will be go to C3, not go to RE. So what the difference between you bypass or not bypass? Who knows?
More gain.
Perfect. If you get a bypass, the gain will be higher. Okay? Without the bypass here, the gain will be lower. So make sure when you're looking into the transistor amplifier, you have to tell me, okay, what the name of this amplifier. common net meter, common base, and common collector. That's the first step. The second step, the relation between the input signal and the output signal. For this common net meter, they will be 180 degrees out of phase. That means input and output will be opposite. And also they can asking you about what the name on the capacitor C1, C2, C3, and the purpose of each capacitor. Right now, we not go into any detail, but at least you're looking technician, you're looking at, you're able to tell what I just talked to you. Any question, any confusing, anything else?
Yes, Mr. Fan, I have a question about C3.
Yeah.
So the main reason that AC go to C3 is because what is the main reason that AC go to C3 instead of RE? Is the difference of impedance between RE and C3?
Now, you understand when you draw for AC, that one will be routed. So you don't worry about C3. Bypass, that means when you ground at meter, so the current go to the ground, not go to the resistor.
Okay, understand that.
So
And
that's
Mr.
why
Mr. Fan, was that grounded or short?
routed, short to route. This is short, that means short to route, right?
Yeah, I understand that if you ground there and you don't have C3, the current is going to be to ground. But my question is, when you have RE and you have also C3, why AC go to C3?
Why does
thought-
the current pull to C3? How does it pull to C3?
The thing is C3 is shorted.
If you guys go back about 4 slides, when Mr. Pham started the class today, that actually is what is shown. For AC is shorted, for DC is open. That was the first slide of today.
That's what I'm saying is when you say shorted, like the wire go to the route. Is it right or wrong?
Right.
Right. So
Or-
that's why
or
the
AC.
current here, they go to the short, they not go to here.
Current takes the flow of least opposition. Which is obviously through the short.
And did somebody say that provides more gain to the amplifier?
If you get the bypass, the gain of the amplifier will be more.
Right. That's the reason.
Now, when I turned it out to the AC circuitry, you didn't see any C3 anymore. Now, this one you really need for the technician. Okay? You understand that you get a 1.8 volt DC here. You see that?
Mhm.
And also you get 100 microvolt sideways at this point also. So basically at the base you get 2 different voltage, one DC and one for AC. So if I want to measure the voltage AC here, at the base. For your oscilloscope, what you set your coupling?
AC coupling.
You must set AC coupling. Why? The thing is 1.8 volt DC compared to 100 microvolt. So basically, the sine wave will be too small inside the DC voltage. If you put a DC coupling, you cannot see this sine wave. So you want to measure the signal, you must set AC coupling. Okay? And that will be the same at the collector here. And collector, you get 6.04 volt DC bias. Also, you can get the sine wave bigger. However, compared to 6 volt, they still more small. So you must set AC coupling. Okay? However, when you're looking at the output here, you see they start from 0 right here. That means they already blocked 6.04 volt with this C2. So only AC here. Okay? That means go to the speaker. Okay? And at the meter here, you see they not show you any sine wave. The thing is they sorted to the right. Look carefully into that schematic and anything you don't know. Just question. The thing is for technician, I don't care what's going on in here, but I care if I get 100 microvolt here, I measure the signal, I supposed to get 100 microvolt. And I measure the output here, I supposed to get opposite sine wave.
Phase shift.
They will be bigger, okay, depending on calculation. And technician, when you measure it, you don't have to do any calculation. Engineer, we already telling you, I want 3 volt peak to peak here. Okay? Only thing you measure here, can you get that voltage peak to peak or not?
So, Mr. Pham, are you also saying that you get like a gain and you get that phase shift? So you get the phase shift and the amplitude is also higher?
Yeah, they opposite. 180 degree output. And the output sine wave will be bigger than input sine wave. That's why.
So you got voltage gain there too.
Yeah. Voltage gain for AC. Any question? Okay. Now, this engineering. You understand it is the collector. This is the base. This is the ammeter. So if you're looking on the DC here, you get 10 volt DC. However, on this AC module, you didn't see any 10 volt. Where 10 volt go to?
This is the AC equivalent circuit, so there's no DC required.
My question is, if you're looking at the DC, you get volt VCC right here. However, when we go to the AC module, You didn't see that 10 volt. Where that go?
Shorted, isn't it?
Yeah. Go back here. Okay. Right here.
Grounded.
They must be routed. On DC source must be routed. So now, if you're looking into the circuitry here, that means AC, they will be routed. You see that? Don't asking me why, okay? You must try understand. Now, at the collector right here. So RC connect from collector to the route, right? That's why they draw RC right here. One side collector, the other side will be routed. You get that?
Yes.
Okay. Now, looking on the next one. C2 you not see in the AC. The thing that they will be shorted.
Yeah.
So what happened to 100K here? They connect.
It's in parallel with since the source was shorted. I mean, since the capacitor was shorted and the source was grounded, those two resistors are now in parallel.
Right. That means 100K, one side connect to collector, the other side connect to route. So that's why they can draw RC IL right here. One side collector, the other side route. That means I try to converting from DC to AC.
So, hey, Mr. Pham, so when RC is in parallel with the RL, you call that what?
RL.
Little, you call it what?
Not yet.
Oh, okay.
Now, I make sure the student understand how come they get RCRL connect this way in AC module. Okay, so for the amplifier, they will focus on gain. That means the gain of the amplifier. That's the first step. The second step, they want to know the input impedance and the output impedance. I'm talking about output impedance. That means you at the output here, you're looking into the amplifier, okay, to see how many resistors. That's what they're talking about, output impedance. Or they can using RL. That means load resistance. Okay, or they can say G out. Doesn't matter. Only thing is, if you want to calculate the output impedance, output resistance, that means you're looking into the amplifier. In this case, I can telling you, they in this book they're using R small c. Okay, that means resistance of the collector. They will be equal RC parallel with RL. So if you want to calculate the output impedance, you take RC times RL divide RC plus RL. That's output impedance. Now, input impedance. Your input right here. You're looking into the amplifier. That's what they call a G in. Looking into the input to see how many resistance. Is it a series or they parallel? So what G in equal?
R1
parallel R2 parallel RE.
R prime E.
Okay, now R1 parallel R2. You understand again. If you're looking on this one, okay, R1 here, one side connect 10 volt, they could be route. And R2, they already connect to the base and route. So that's why they parallel. Okay, R1, R2 parallel.
0.
Now, R prime E, that means the internal resistance. Okay, but you have to get one resistance from the base into the route. That's what they call a RB. Okay, so let's see what they're telling you here. Okay, they not giving you that, they don't care. Okay, however, you can see G in will be equal R1 parallel R2 and parallel RB. Okay.
Hey, Mr. Pham, I'm having a hard time understanding what RB. I can see the RE because the RE is 25 millivolts over IE.
But what I'm saying here, R prime E internal resistance.
Right.
Internal resistance. But the one resistance you can see, that means the one from the base to the route, and they call RB. How do we calculate the RB?
IE times RE prime.
Law.
V divide I.
VB.
IB. Yes.
Okay. And what VB equal?
The voltage from base to ground.
VB is 0.
VB. We already did it. IE time R prime E, right?
Yes.
Divide to IB. And also IE equal 1 plus beta time IB time R prime E. Everything divide IB. And IB cancel out. So basically RB will be equal 1 plus beta time. Okay?
Okay.
You want to calculate the RB, and that is the formula. 1 plus beta times R prime E. But try to understand, this is the formula to calculate the input resistance of the CE amplifier. And if you want to calculate the gain, then there will be V out divided to V in. On this one, okay, now, you see on this circuitry, they given you beta DC 150, beta AC 160. And this is the input here, 10 millivolt IMF. And this is the output. First thing you can see, the input and the output will be 180 degrees of phase, right? Opposite,
Right.
okay? Let's see what they want.
Input is RMS and the output is peak too.
Okay. And now they given you this DC bias, and they want to calculate the VB, VE, IE, IB, IC, VCC. You already know everything. And also R prime E, 25 millivolt divided to IE. Now, they given to you that one. They want to calculate for the CM amplifier. R prime E, we already calculated, they will be 6.58. If you want to calculate the R in base, okay, so they will be on that one. I don't know. The thing I don't know, when I run by iPad, some they not display. Let's see.
RE is ohm and the other one is beta AC.
Okay. Beta AC times R prime E. Right. They not display a beta. And this one they not display O. Okay. So if you want to calculate the R in the base, and you get beta times R prime E. Basically, the formula I just given to you, 1 plus beta. But in the textbook, they ignore number 1. And if you want to calculate the total input impedance, then R1 parallel to R2, okay, and parallel to R in base. That's what they call a G in. Either way, you can say R in total, or you go G in, input impedance. Output impedance, you take RC parallel RL, and that's the same thing like you said G out, output impedance. The gain of the CE amplifier will be equal RC. That means this guy here divide R prime E. Okay, so they want to determine AC value for the CE amplifier. So what they want They want you to doing calculation here. Can you get everything done in 10 minutes? If who can get that for me, I can put it in here for the student.
Which circuit are we looking at, Mr. Pham?
I see I can get you guys answer or not. Okay, that one equal 6.58. R in bay 1.05K. R in total 873. Out 833. AV 126.7. V out equal AV times V in equal 1.3. Okay, so that is any question, anything on the CE amplifier? You done? Otherwise, we go to the next one. Now go to the CC amplifier. Common collector. When you see a common collector, that means collector will be routed in AC. Okay? Like we said, common emitter will be routed. Common collector will be routed in AC. And they get another name. They call an emitter follower. So either name That means common collector. Okay, so they say collector ESAC ground, stable voltage gain, and they will be a high input impedance and will be low for the noise distortion. That's the characteristic for common collector. Okay, this is how the circuitry. For a common collector, input applied to the base. Output will be coming from admitter. That's why they call it admitter follower. And you get a capacitor C1, C2. And C1 or C2, same name, DC blocking, AC coupling. And the input and the output, you're looking into that, and they will be in phase. You see that? That input, that output here, in phase, both going up or both going down. So when you're looking into the circuitry, they apply input to the base, output from the admitter, and you must know that is a common collector or admitter follower. Same thing. You get the base here, and you get the admitter here. Okay? And this collector will be routed. So the current still beta IB. Okay? And this is from the base to the admitter. You get the R prime E. That means internal resistance from the base to the admitter. And outside, you can get RE. You can get this one and this one in parallel. This one is supposed to be shorter. Okay? So, same thing. If you want input impedance, that means you're looking here into the transistor. That will be input impedance. You're looking in this way, you can get output impedance. And they given to you R in base will be beta, I believe so.
Yes, it is.
Beta time on your will be okay. This will be beta. And this will be beta. Okay? R in base. Okay? Basically equal beta time RE. What is the RE here? That will be R big E parallel QR load. I already explained to you right here. As Ricky, if you want to calculate the input impedance, they will be equal R1 parallel R2 parallel to R in of the base. Okay. Voltage gain equal R small e divide R prime e plus R small e. And if you want the V out, then they will be AV times VE. Okay, what I want you to do, doing this calculation for me. If you have a no question, that means I suppose you know how to do your calculation when you get the formula. Okay, then I can give you the answer. The thing is, take a long time to do your calculation. Okay, VB, quickly. You can tell me right away. When you get a 10 volt here, and this register the same, they
5
just
volts.
divide by 2.
5 volts.
5 volt. And VA 4.3, right? And IA will be 4.3 milliamp. VEC equal VCC, 10 volt. VCA equal 10 minus VE. VE 4.3. RE 500 ohm. No, RE 5.8 ohm.
$5.8.
Okay, this one is output impedance. Okay, 500 ohm, right? R in bay, 87.5K. Total input impedance, 8.16K. AV, the gain, 0.989. And VO, 0.989. So basically, this amplifier have no gain. Input, output almost the same. The gain for the common collector normally less than 1. However, input, output, they not inverted. They in phase. And they will be get the input impedance will be higher. So that depending on the configuration when they design the circuitry, they know which one they wanted. If you want more gain, then you better using CE amplifier. If you want a high input impedance, then they can using C amplifier. You done? Copy done yet? Okay. The last one. Quickly. We get about 10 more minutes. Then you take a
Mr.
quick.
Pham, can I see that circuit be, yeah, that one right there, right there, right there.
I just copy from this side. To put in here.
Okay, thank you.
Come on, Bay. Bay is at a AC route. Input by the admitter and output from collector. No current gain, but high voltage gain. Low input impedance, high output impedance. High frequency application. You can read that. Okay, I quickly go here. For this common base, input applied to the admitter and output from the collector. Input output will be in phase. And if you want to calculate the gain, then they will be RC divide R prime E parallel R big E. If you want input resistance R in, they will be R prime E parallel R big E. Output resistance R out, RC parallel to RL, the same like admitter. C1, C2, DC blocking. And this will be on up the calculation, okay? And we already given to you formula. You're able to calculate it. And this I just copy, okay? Next one, Darlington connection. That means if you see the transistor connect this way, they get the name a Darlington connection. What this circuitry for?
High current amplification.
You want to get the high gain, current gain, okay? For this one here, okay, the output coming out here will be beta 1, okay? Time, okay? IB, right? And this one a beta 2, time IB. If you get a beta 1, 100, beta 2, 100. So the gain will be 100 times 100. That only thing they want big current. So that's why when you're working on this circuitry, you have to be very, very careful. The thing is a high current. If your probe valve connect into transistor, they will be burned right away. Okay? And they get a two different here. That means they put every two into one pocket. Okay? And then they connect to different transistor. Darlington transistor are manufactured with the transistor in one case. That means one case they get inside two transistor. This is the way you can do it by get two transistor and make a connection. Okay. But the thing in the field, they just given you this picture. They just ask you the name. What is the name? That will be Darlington connection. And the reason they want it, they want more current. Okay. So this circuitry will get very high current. Okay. So
and the voltage stay constant, Mr. Pham, in this circuit?
Can you say again?
But I understand about the current, but what happened with the voltage? Stay constant?
They don't care voltage.
Okay, so, okay, got it.
On this one, they only care telling you big current. That's it. When they connect into the circuitry, you can see.
So Mr. Pham, so by itself, when it's by itself, just a single base, common base amplifier, there is no current gain, right? But when you put the two together, which is now a Darlington, you actually get very high current gain. Is that what you're saying?
Yeah, they get a higher voltage gain, right? What I said here.
No current gain and very high voltage.
Current does not gain, but the voltage will be gain.
Right. So when you put the two together, as in a Darlington, you're saying you gain a very high current gain?
No, that's quite different. Darlington, nothing to do with that.
Okay.
But wherever you're looking into that, okay, transistor here, I want you to make sure you know the name of that circuit. And also what is the purpose. That means they want more current, okay? The thing is first, transistor, you get a gain equal B1. The next you get a gain B2. And the total gain will be B1 times B2. You can see that they can go very big, 100 times 100.
Okay.
Okay?
Yeah. One more question about the circuit, Mr. Pham. What's happened with the phase, the relationship between input output phase?
No, nothing. In phase.
Okay, thank you.
Only thing is they get a big gain for the current.
Hey, Mr. Pham, would that be something that they would use in a power supply?
Yeah, one of the application. Wherever they need more current. Okay.
Mr. Pham, can a Darlington transistor be configured as a common emitter, common base, or common collector?
What do you mean? Withdraw?
Well, Darlington is just a high beta transistor. And can't you put it in a common emitter, common collector, or common base circuit?
You mean you take the Darlington pair, put it in?
Put it in a common emitter configuration, or a common base, or a common collector.
Nothing to do with that common base emitter or collector. If you want, you can connect outside.
Mm-hmm.
That means the current coming out from common emitter, common base, or whatever, you can connect into the Darlington pair so you can get more current. But they're not related anything to that common emitter, common base, or common collector.
So where's the input usually go in then?
Now depend. Sometime, someday I can get a circuitry they using that application.
Mm-hmm.
Okay. Okay, so now doing this one. You understand number 5? They're talking about two diode. One will be from the base to the emitter. One will be from the base to the collector. On this page you get it done, let me know. I think I get a little problem for the timer. Oh, Okay, so I will be giving you the answer. If you get the question, let me know.
Mr. Pham, can you explain why number 2 is C?
Okay, number 2. For the circuit so, if VCC increase the base current, a no change. The thing is the base current depending on 3 volt VBB and resistor RB. Okay, no matter what beta IC can be, VCC can be changed, but it not affect into the current IB. IB equal VBB minus 0.7 divide RB. Make sure if you get question, then just let me know. Okay, I can tell you on this thing. The transistor is saturated and the base current increase. The collector current will be. You know why collector current will be no change. You know why? Let me know.
Because it's on the active region. The IB is horizontal, or IC is horizontal for IB.
Because VCE is 0.
Okay, now you get the formula IC equal beta IB, right? That current only apply to the active region only. When they be amplifier, then you can using that formula. When they saturated, you cannot get any gain for the current IC. So that's why they say not change. Okay. If IC in the circuit so and reduce in the value of IC saturation will be increased. The thing is, when you decrease the value of the RC, that means the current will be increased. Bias condition for transistor BU in linear. The answer will be one diode will be forward and another diode must be reverted. If the input transistor 5 volt IMS and input 100 millivolt, then the answer will be C. You take 5 volt divide 2 millivolt must be changed to volt. You cannot divide voltage into millivolt. So the answer will be 50. If the bare emitter junction is open, then the collector voltage will be equal VCC. Okay, so this is a calculation here. So make sure you get that calculation. If you're not, then you can watch the video when we upload it. And the same thing here. That's the minimum you must be know how to do calculation when you see this type of circuitry.
Mr. Fan, could you please go back 1 second to the previous slide?
That one?
Mr. Pham, can you give me the formula for number 10? How you got 34.6?
Number 10. They want IE, right?
Right.
So basically you can get IB, right?
You're right.
4 minus 0.7 divide 4.7.
Mhm.
Then you can get IC. You see, you get a collector 8 volt and you get a 24 VCC. So IC equal 24 minus 8 divide to RC for 70 ohm.
Right, that's fine.
You get IC, you get IB, you add them up, you get
Oh, okay.
IE, okay?
Okay, okay, yeah.
You gotta understand it, the quiz. That means just a very basic. When you're looking into the circuitry, you know right away what to do. That is ready for you for interview the job for technician. Okay, and that one,
Just a voltage divider.
every time you get the quiz, you get 100%, you perfect. Ready for the technician job. If you get less than 70%, need to do more. Okay, this is the last one. Okay,
Can you go back one page, sir?
what?
Can you go back one page? I didn't quite see the answer. 2, 3, 5. Okay.
Number 13 is number 16. No, that was just a typo, Mr. Pham. You meant to say 16 for 16, but you said 13.
Okay, 12, 13, 14, 15, 16. Okay, yeah, thank you.
Thanks.
You see a lot of work trying to prepare this thing. So that's why typo sometimes.
Okay, I give you Easter money for that one, Mr. Pham.
I'm not getting 100%, so I guess I better go study.
I'll give you Easter money.
Only thing is you get over 70%, you okay. If you get 1%, quit it.
That's funny.
Just quit.
Only thing I want you to study.
If we go back 1%, go back, Mr. Pham.
Yeah, you retire with me and Mr. Pham.
Okay, but I know for a few moments we will be back into the classroom. Okay.
Don't give us false hope.
You got to get your needle shot, Mr. Pham, first.
Okay. At this time, I teaching the guy, and also I have to teach the guy how to do the left one also. Okay? So, good night.
Good night. Thank you
Good
very
night.
much.
Thank you.
Thank you.
Yeah, welcome.
Good night. Good night. Thank